or framework consisting of a number of connected triangles. After completing this module, you will be able to apply the procedure of triangulation to estimate the extent of land, describe the methods of computing the chain angles. Let's observe the step-by-step description to measure the area of the given field by chain triangulation. As a first step, gather these instruments: a chain of 20 or 30 meters, arrows as required, ranging rods as required, and pegs as required. Identify the field whose area is to be measured. Now, establish the survey stations. As you know, the survey station is a prominent point on either at the beginning or the end of the chain line. Look, in this field, A, B, C, D, and E are the main survey stations. You know that any line joining the main survey stations is called a main survey line. The biggest of the main survey line is called the baseline. Mark the baseline as it helps you to take command of the field. That is, it acts as a reference line. Mark this baseline with chalk powder. You know that any line joining the main survey stations is called a main survey line. The biggest of the main survey line is called the baseline. Mark the baseline as it helps you to take command of the field. That is, it acts as a reference line. Mark this baseline with chalk powder. Divide the area into triangles. Note that with the baseline, one triangle EDC is already formed. Using the chain, if you join the points A and C, you will get two more connected triangles, CAE and CAB. Look, this framework now gives three connected triangles. One is A1 connecting EDC, the second is A2 connecting CAE, and the third is A3 connecting CAB. Once you have the area of each triangle, you have to sum up the areas of all triangles. Here, we have areas of three triangles, A1, A2, and A3. When we sum up the area of these three triangles, A1, A2, and A3, we get the area of the given field, that is, ABCDE, as equal to 217.95 square meters. Assume that there is a pond in this field. Using a chain, you cannot form triangles in this field with a pond. In such a case, the angles between adjacent sides are fixed by chain angles, either by tie stations or a cord. Let's understand the formulation of any one chain angle for the field ABCDE using the tie stations. On the main survey line AB, fix the tie station T1 at some distance, say 3 meters from A. Now, hold the handle at the main survey station A and fix another tie station T2 on the opposite main survey line AE, but at the same distance as above. In this case, it is 3 meters. Use a tape or chain to measure the distance between T1 and T2. Measure the distance between T1 and T2. Now, the principle of chain survey or chain triangulation is to provide a skeleton or framework consisting of a number of connected triangles. The steps for estimating the extent of land using chain triangulation are: Step 1. Gather the instruments. Step 2. Establish the survey stations. Step 3. Establish the baseline. Step 4. Divide the area into triangles. Step 5. Measure the length of all lines. Step 6. Calculate the area of each triangle. Step 7. Calculate the sum of the areas of all the triangles. The two methods of computing the chain angles are by using tie stations and chord. You have seen that surveying is a method of showing the relative positions of objects on the ground. Do you know, by showing the relative positions by means of offsets and oblique lines, you can locate ground features? Let's find out how we can locate ground features by going through this module. Locating ground features. Welcome. After completing this module, you will be able to identify the types of offsets, state the use of different survey lines and running perpendicular lines to a survey line from a point, and an offset is basically a distance measured from a survey line to a certain point or object located on one side of the line. Offsets are taken to know the distance between a survey line and a point or an object. For example, on this plan, let us take a look at how we can know the distance from the baseline to each of the points A and B. As there are no obstacles between the baseline and A, you simply need to run a line from the baseline to the point A, so that it is perpendicular to the baseline. This perpendicular line is called the perpendicular offset. But what about an offset to connect B with the baseline? As you can see, there are obstacles between the baseline and B, making it difficult for a perpendicular offset to be taken between the baseline and B. So, you must take an offset from the baseline at a point which is closest to B, although not perpendicular to it. Such an offset is called oblique offset. So, remember, the two types of offsets are perpendicular offset and oblique offset. The perpendicular offset is taken when there are no obstacles in between from the baseline, and the oblique offset is taken where there are obstacles in between. When taking offsets, the survey lines we must mark on the ground are the baseline and the check lines, or the lines running to the offsets. As the baseline runs across the central region of the area, identify and mark it correctly on the ground so that you can run the check lines or the offsets from it. Once you have taken the perpendicular offset and measured it with a tape, you can show it on the survey plan as a check line. In order to take an oblique offset from the baseline, identify the point on the baseline that is the closest to the oblique offset point, without any obstacles in between. Once you have measured the oblique offset, you can show it on the survey plan as a check line. So, remember, the baseline and the check lines are the important survey lines while taking offsets. You can use the cross staff to take the perpendicular offset and the chain to take the oblique offset. We've had a look at the types of offsets. Now, let us find out how to locate ground features using the chain or tape and offsets. Suppose you have the plan of an area and have to locate a feature on the ground marked by it, such as this pit. By running offsets at the opposite ends of the pit, points A and B, you can locate the pit on the ground and check whether its position is correctly shown on the map. The perpendicular offset to A can be taken at A by setting a cross staff at the baseline directly opposite it, and then running a chain or tape to it. And an oblique offset can be taken at B by running a chain or tape from B to the point on the baseline nearest to it. By comparing the lengths of these offsets with those on the plan, we can check whether the position of the pond is correctly shown on the plan. So, remember, by running offsets on the ground with the help of cross staff and chain or tape, you can locate ground features and check their position on plans. In this module, you have learnt how to identify the types of offsets, the use of different survey lines, and running perpendicular lines to a survey line from a point, and to locate ground features using the chain and offsets. The two types of offsets are perpendicular offsets and oblique offsets. The cross staff is used for running perpendicular offset. The chain is used for running oblique offset. When taking offsets, the survey lines we must mark on the ground are the baseline and the check lines. We can use the cross staff and the chain to run offsets so that we can locate ground features. The first of these methods is the average offset method. With this method, you can compute the areas of regions with irregular boundaries made of straight lines by taking perpendicular offsets. First, run a long line from one end of the area to the other. Then, divide the line into equal chainages or distances. Measure the equal distances with a chain or tape and mark equal lengths by driving arrows into the ground. To the extent possible, try and keep the chainages equal. Then, take the perpendicular offsets by placing the cross staff at equal chainages. The distances you obtain in this way are called ordinates. Ensure that you take the offsets in such a way that the end of one ordinate is joined to the other by a straight line of the irregular boundary. Once you have the required number of offsets in the area, you can calculate the area with the formula. To follow the mid-ordinate method, you must draw ordinates at each of the points of division of the baseline. To obtain the required area, multiply the average of these ordinates with the length of the baseline. For example, the trapezoidal rule is applied in the case of areas where each part is assumed to be a trapezoid. The trapezoidal rule can be stated as follows. To the sum of first and last ordinates, add twice the sum of intermediate points. Multiply the total sum thus obtained by the common distance between the ordinates. 1/2 of this product gives the required area. Simpson's rule is applied in areas where the boundary lines are like curves and arcs. The rule can be stated as follows. To the sum of the first and last ordinates, add 4 times the sum of the even ordinates and 2 times the sum of the odd ordinates. This sum, multiplied with 1/3 of the common interval between the ordinates, gives the area. As the results obtained by using Simpson's rule are more accurate, it is used when greater accuracy is required. If trapezoidal and Simpson's rule are to be applied, then note that the interval between successive ordinates must be uniform throughout the length of the baseline. If the interval is not the same, divide the baseline into different sections, each having the same interval. Calculate the areas of each section separately and add them up to get the required. In this module, you have learnt the steps involved in field data entry and cross-staff survey for estimation of areas, and also to find the area by using chain and offsets. In the average offset method, the area is computed by dividing the baseline into equal chainages and taking perpendicular offsets by placing the cross-staff at equal chainages. In the mid-ordinate method, ordinates drawn at each point of division of the baseline are used to compute the area. In the trapezoidal rule, this formula is applied to compute the area. Similarly, this is the formula to be used for computation of area by the Simpson's rule.
To know the extent of land with a cross-staff, you must first establish the base line of the area. To mark the baseline, run the chain over the center of the area, connecting the 2 main stations that are the farthest apart. Then, set the cross-staff at a point on the baseline so that you can sight 2 main stations, one at the end of the baseline and another that is the closest to it. If needed, adjust the position of the staff on the baseline so that your line of sighting to one station is exactly perpendicular to the other. Mark the point on the baseline and measure the length from it to the survey station. As you know, this position is called the offset. In the same way, move down the baseline and mark the other points on it that connect it to the other offsets, and take the respective measurements. By drawing lines from the baseline to the offsets, you can divide the areas into triangles and quadrilaterals. You can now find out the total area of the land by adding up the areas of all these shapes. So, let us find out how to calculate the areas of the shapes. We can calculate the areas of the parts into which the site has been divided by using standard mathematical formulas. Let us find out what they are. If some of the parts are divided into right-angled triangles, their area can be calculated with the formula area is equal to half base into height. The formula for calculating the area of the parts in the shape of a trapezium can be given by the formula half the sum of A and B into H, where A and B are the parallel sides and H is the vertical line joining them. With the help of these formulas, we can calculate the areas of the parts of the site and add them up to obtain the entire area. In this module, you have learned how to use cross-staff survey for finding the extent of land. To find the extent of land with cross-staff survey, you must carry out a number of steps, such as marking all survey stations, running a chain along the baseline, setting the cross-staff along the baseline, taking offset measurements, dividing the area into parts. The whole of the area can be computed by summing up the areas of all the parts.
You know that chaining is a standard technique used in surveying to measure distances between objects so that their relative positions can be shown accurately on a map or plan. Sometimes, surveyors encounter some basic problems when they are trying to obtain points of reference at places other than the chain line. So, what are these basic problems in chaining? How can we solve them? Let's find out the answer to these questions in this module, Basic Problems in Chaining. After completing this module, you will be able to apply the procedure for erecting a perpendicular from a point on a chain line, dropping a perpendicular from a point to a chain, and running a... The first of the basic problems in chaining is erecting a perpendicular from a point on the chain line. The perpendicular can be erected by a method called the 3-4-5 method. Let us find out what this method is. In this method, a measuring tape is shaped into a right-angled triangle so that the triangle's base begins at the given point on the chain line and the triangle's top is perpendicular to the given point. Let's see how this can be done. First, mark the point on the chain line at which the perpendicular is to be erected with an arrow. Let this point be B. Mark another point C on the chain line such that B is 3 feet or 36 inches from C. Keeping the 3 feet mark held at B, roll out the tape vertically above B up to the 7 feet or 84 inches mark. Let's say this is point A. With A held straight above B, extend the tape back to C. You'll see that the reading at the extended end of the tape at C is 12 feet or 144 inches. As you can see, you have formed a right-angled triangle ABC with the tape. As a result, any point on AB will be perpendicular to BC at B. This method is called the 3-4-5 method because a tape length of 12 feet is shaped into a right-angled triangle having sides measuring 3, 4, and 5 feet. So, remember, to erect a perpendicular point from a point on the chain line, follow the 3-4-5 method. The second basic problem in chaining is dropping a perpendicular from a point to a chain line. Here, let's say AB is the chain line and C is the point from which the perpendicular is to be dropped. Mark any point on the chain line with an arrow. Let this point be D. Take a line dory that is equal to the length of CD. Then, holding that length of the dory, mark another point E on the other side of C on the chain line such that CD is equal to CE. Measure the length of DE along the chain line. Mark the midpoint of this length. Let this point be F. The line CF will be perpendicular to the chain line AB as the lines CD and CE are equal sides of the isosceles triangle CDE. So, remember, to drop a perpendicular from a point to the chain, mark equal lengths of line dory on either sides of the point on the chain line. The line from the point to the midpoint of these two marks will be perpendicular to the chain line. The third problem in chaining is that of running a parallel line to a chain line through a point. Here, for instance, let C be the point through which a line that is parallel to chain line AB must be run. So, first drop a line from C to a point D on the chain line so that CD is perpendicular to the chain line. Take the measurement of CD. After that, Mark a point E on the chain line and erect a perpendicular at point F so that EF is equal to CD. Join C and F. The line CF runs parallel to the chain line AB. So, remember, to run a parallel line to a chain line through a given point, drop a perpendicular to the chain line from that point. Then, erect a perpendicular to another point of the same length from the chain line, joining. In this module, you have learnt that the basic problems in chaining are erecting a perpendicular from the chain line, dropping a perpendicular from a point to the chain, and running a parallel to the chain line through a given point. To erect a perpendicular point from a point on the chain line, follow the 3-4-5 method. The top of the right angle triangle is the perpendicular point. To drop a perpendicular from a point to the chain, mark equal lengths of line dory on either sides of the point on the chain line. Let's say you have to measure the horizontal distance between points A and B, which are separated by this hill. These stations are not intervisible because the hill is the obstacle to ranging. Note that there is no obstacle to chaining, as you can carry out stepping on the slopes of the hill. To overcome the hill as an obstacle, set stations C and D between A and B. Ranging between A and B is obstructed by the hill, but you can carry out stepping with the chain from A to the intermediate station C and from the intermediate station D to B. After that, add the horizontal distances of AC, CD and DB to obtain the distance between A and B. Now, take a look at the points M and N. There is a large rock between them, so ranging cannot be carried out. But you can run a chain along the horizontal from M towards N up to the point directly opposite N, which is O. After that, run the chain from N to O. In this way, you obtain a right-angled triangle MNO. As MN is the hypotenuse of the triangle, you can calculate its length with the formula MN is equal to under root MO square plus ON square. So, now let's say you have to find out the distance between 2 points A and B with a building between those points. Here, the building is the obstacle to both ranging and chaining. Note that the building is an upright structure, so it is impossible to set intermediate survey stations or run a chain along its surface. So, you can set the cross staff at A and mark a point C so that line AC is perpendicular to line AB. After that, set the cross staff at C and mark a point D so that line CD is perpendicular to line AC. Note that you should mark D at a place beyond both the obstacle and point B. Set the cross staff at point B and mark a point E on line CD so that line BE is perpendicular to line CD. Now, you can see that AB is equal to CE. So, to know the distance between A and B, just measure the distance between C and E. So, remember, to overcome an obstacle to both chaining and ranging on a line, run 2 perpendicular lines of equal length, one before and one after the obstacle. After that, join those points and measure the length of the joining line. In this module, you have learnt how to solve the problems whenever obstacles occur in chain survey. To overcome obstacles to ranging but not chaining, you can use the chain for stepping or triangulation. To overcome obstacles to chaining but not ranging, first obtain 2 similar triangles. After that, calculate the distance by equating the ratio between the corresponding sides of the similar triangles. To overcome an obstacle to both chaining and ranging, mark points to get perpendicular lines before and after the obstacle. After that, join those points and measure the length of the joining line. The do's and don'ts in chain survey are basically a list of precautions to be taken in chain surveying. Let's find out what they are. Firstly, the surveyor and the leader should have complete and correct knowledge about chaining and the signals used for ranging. Otherwise, you cannot carry out chaining and ranging correctly and efficiently. Always erect ranging rods vertically. Do not leave them on the ground at an angle. Also, use colored flags on the top of ranging rods so that they are clearly visible. Otherwise, you will have difficulty in seeing the survey stations. Always use the correct technique of unfolding and folding the chain every time. Otherwise, the chain might get tangled and the links might also get stuck. Do not displace arrows from their correct positions. Otherwise, you will take measurements from wrong points on the ground. Always take the readings from the correct end of the chain. Otherwise, you will get incorrect measurements. Lastly, take care in reading and calling out the values of the measurements loudly and clearly. Otherwise, the measurements might not be recorded correctly.
1 meter,
1,
2 meters,
2 meters,
3 meter,
3,
4 meters,
4,
5 meters.
5.
So, remember, always follow these do's and don'ts in chain surveying to ensure that you get the best results from your survey. In this module, you have learned the do's and don'ts that need to be followed in chain surveying. The surveyor and the leader should have complete and correct knowledge about chaining and the signals used for ranging. Erect ranging rods vertically with colored flags. Use the correct technique of unfolding and folding the chain and take readings correctly and call them out loudly and clearly. Do not displace arrows from their positions and do not count chain lengths incorrectly.
We have already seen the parts of the prismatic compass. Before you can use a prismatic compass for survey operations, you must make some temporary adjustments to it. The step-by-step procedure to adjust the prismatic compass is as follows. Fixing the compass to a tripod. Centering the compass. Leveling the compass. Adjusting the prism. Observation of bearings. Firstly, adjust the tripod to a suitable height for observation by spreading and contracting the legs of the tripod. Place the prismatic compass on the threaded top of the tripod. Now, turn the compass box clockwise to fix it to the threaded top. Determine the center of the prismatic compass by either dropping a piece of stone from the bottom of the compass box to the ground, or suspending a plumb bob from below the compass box to the ground. Now, level the prismatic compass by using the ball and socket arrangement provided on top of the tripod. Loosen this arrangement and place the box in such a way that the graduated ring should rotate freely without touching either the bottom of the box or the glass. Move the prism up and down till you can see the figures on the graduated ring sharply and clearly. Finally, bisect the ranging rod at the required station perfectly by sighting through the prism slit and horsehair at the sight vane. In this module, you have learned to apply the temporary adjustments to the prismatic compass. Firstly, adjust the tripod to a suitable height for observation by spreading and contracting the tripod legs. Center the prismatic compass by either dropping a piece of stone from the bottom of the compass box to the ground, or by suspending the plumb bob. Level the prismatic compass by using the ball and socket arrangement provided on the top of the tripod. Move the prism up and down till you can see the figures on the graduated ring sharply and clearly. Finally, bisect the ranging rod at the required station perfectly by sighting through the prism slit and horsehair at the sight vane. In this module, you have learned to apply the temporary adjustments to the prismatic compass. Firstly, adjust the tripod to a suitable height for observation by spreading and contracting the tripod legs. Center the prismatic compass by either dropping a piece of stone. You have seen that the direction of a survey line can be shown with respect to other survey lines or with respect to a fixed meridian. You also know that if the directions are shown with respect to a meridian, then they are shown on the map or plan with bearings as the measurement. Let us suppose you have a map or plan that shows the measurements of all survey lines only in terms of bearings, whereas you require knowing the measurement in angles. How would you compute the angles from bearings? Let us find out the answer by going through this module. Welcome! After computing this module, you will be able to compute angles from bearings. Take a look at this area. As you can see, there are 4 main stations. When this area is shown in the form of a map or a plan, this is how it looks. The 4 main stations are marked with the letters A, B, C and D. Note that the point N on the map is not a main station, but the magnetic north of the area. We know the bearings from the magnetic north to every survey line within the area, as we have already calculated them with the help of the compass. So now, let us start computing the angles based on the measurement of the bearings. To begin with, let us find out angle AOB. We can say that angle AOB is equal to the difference between bearing OB and bearing OA. Note that these bearings are in fact the arms of the angle AOB. From the diagram, we can see that bearing OB is equal to 132 degrees, 30 minutes, and that bearing OA is equal to 50 degrees, 30 minutes. Therefore, we can say that angle AOB is equal to 82 degrees, 30 minutes. Similarly, if we have to find out angle BOC, we can say that it is equal to the difference between bearing OC and bearing OB. From the diagram, we can see that bearing OC is equal to 232 degrees, 30 minutes, and that bearing OB is equal to 132 degrees, 30 minutes. Therefore, we can say that angle BOC is equal to 100 degrees. Similarly, we can say that angle COD, which is the difference between bearing OD and bearing OC, is equal to 87 degrees, 30 minutes. But angle DOA has to be calculated in a different manner, because it is in a different quadrant after the whole circle bearing. So to calculate angle DOA, you have to use the formula. Angle DOA is equal to 360 degrees minus bearing OD plus bearing OA. So angle DOA is equal to 360 degrees minus 320 degrees, 30 minutes plus 50 degrees, 30 minutes, which is equal to 90 degrees. To check whether the angles calculated from the bearings are correct, you must add them up and see whether they add up to 360. So let us add angle AOB, angle BOC, angle COD and angle DOA. This is equal to 82 degrees, 30 minutes plus 100 degrees plus 87 degrees, 30 minutes plus 90 degrees. As this sum is equal to 360 degrees, we can say that the angles computed from the bearings are all correct. So remember, this is the procedure for computation of angles from bearings. In this module, you have learnt how to calculate angles from bearings. To calculate angles from bearings, calculate the difference in the bearings forming the arms of the angle. To calculate an angle from a bearing in a different quadrant after the whole circle bearing, subtract the bearing measurement from 360 degrees and add the measurement of the complementary bearing to the difference. You have seen how to compute angles from bearings while carrying out the survey of a site using a compass. Now, let us say you have a map or a plan which shows measurements of the included angles between successive survey lines and the measured bearing of the initial survey line. Based on these data, if you are required to calculate the bearings of the subsequent survey lines, how would you do it? Let us find out the answer by going through this module. Welcome! After completing this module, you will be able to compute. Let us begin by taking a closer look at the map. A, B, C and D are the included angles which have been measured clockwise from the respective backstations. Theta 1 is the measured bearing of the survey line MN. We know that the bearing at the initial survey line MN is theta 1 and that the first included angle is A. We can calculate the bearing of the next survey line. NO with this formula, bearing NO, that is, theta 2 is equal to the theta 1 plus A minus 180 degrees. Similarly, the bearing of the next survey line OP, that is theta 3, is equal to theta 2 plus B minus 180 degrees. In the same way, the bearing of the next survey line PQ, that is theta 4, is equal to theta 3 plus C minus 180 degrees. However, to compute the bearing of the survey line QR, that is theta 5, we have to use the formula theta 4 plus D plus 180 degrees. 180 degrees are added rather than subtracted to compute the bearing of a line whose included angle is not measured from the meridian from which the bearings are to be computed. As you can see, the included angle D has not been measured from the meridian at Q. It has been measured with reference to the survey line QR. So remember, in this module, you have learnt how to calculate bearings from angles. To calculate bearings from angles, add the included angles to the bearing of the preceding line. If the sum is greater than 180 degrees, subtract 180 degrees. If the sum is forebearing means the bearing of a line as measured in the direction in which the survey progresses. Back bearing means the bearing of a line measured in the direction opposite to the survey. For example, in the figure A, B, C, D, E, where the survey progresses clockwise from A to E, theta is the forebearing of the survey line AB and theta 1 is the back bearing of that very line regarded as line BA. Note that in the whole circle bearing system, the difference between the back bearing and forebearing must be equal to 180 degrees. So, in the example we have seen above, the forebearing of line AB is 55 degrees and the back bearing of line BA is 235 degrees, 180 degrees more than the forebearing. So, in this module, you have learnt the concepts of fore and back bearing. Forebearing means the bearing of a line as measured in the direction in which the survey progresses. Back bearing means the bearing of a line measured in the direction opposite to the survey. The relation between forebearing and back bearing is that back bearing is equal to forebearing plus or minus 180 degrees. You have seen that the compass is a useful instrument for calculating bearings. Interestingly, the compass can also be used along with a tape or chain for a type of survey called traversing. So, what is traversing and why is it important? Let us find out in this module. Applications of compass survey in the field. After completing this module, you will be able to explain the importance of traverse in surveying and perform the compass traverse adjustments. Often in surveying, irregularly shaped ground features such as ponds or lakes, or rivers or roads need to be surveyed. To do so, you should run a series of survey lines along or around the outline of these ground features so that you obtain the correct framework of the survey. As such lines typically run in a zigzag pattern, the compass, along with the chain or the tape, help you to take accurate measurements of their varying directions and lengths. This type of survey, in which several connected survey lines of known direction and length form the framework, is called traversing. You have just seen that you can depict the irregularly shaped ground features like lakes, rivers or roads with the help of traversing. When the connected survey lines form a loop or a polygon around the ground feature, as in the case of a pond, it is called a close traverse. When the connected lines form an unjoined pair along the ground feature, as in the case of a river or a road, it is called an open traverse. Often, when a closed traverse is plotted based on measurements taken in the field, the end of the last survey line of the traverse does not exactly meet the starting point of the traverse. This error is called the closing error. It occurs due to errors in measuring distances and angles on the ground.
नमस्कार, मैं दिव्यांशी चौहान।
नमस्कार, मैं भगवती जबनाल। आप सभी का सीएससी कड़ी की तीसरी चर्चा में आपका स्वागत करते हैं।
हमने अभी तक बात की सीएससी सेवाओं के बारे में, जिसमें त्यागी सर ने हमें सीएससी का एक ओवरव्यू दिया। साथ ही हमने बात की पीएमजी दिशा योजना के बारे में।